Good morning and welcome to our first lesson on our functions and graphs topics. The first topic that we're having a look at is this idea of direct proportion. A quick little reminder that two variables are linearly related if the graph is a straight line, and that's really it. The graph just simply needs to be a straight line, and then the two variables are linearly related or linearly connected. In the textbook on page 12, there's a taxi charge scenario that's described, and I've put the cost versus the distance travelled table here. And what you can see is that if we travel 0 kilometres, then it's still going to cost $4. So that would be the reasonably hypothetical scenario of hopping into the taxi, hopping straight back out. They're going to charge you $4 for the privilege of doing that. Then we can see that we add $2 for each kilometre. So if we travel 1 kilometre, then the cost is going to be $6, which is our initial $4 plus the $2 kilometre charge. And you can see that we're adding a constant to each time. And what you might recognise is this is actually an arithmetic sequence where our initial term is A and our constant difference is 2. We need to be careful about thinking about them as arithmetic sequences, though, because our first term is actually theoretically our 0th term, and we don't know how to deal with that in arithmetic sequences at the moment. And in fact, we won't. But you should recognise that the numbers form an arithmetic sequence. In terms of the geometry of an arithmetic sequence, if you plot the terms of an arithmetic sequence, any arithmetic sequence, it will come out as a straight line. So the graph of the taxi cost is shown here for you. One thing I don't like about this graph is it's missing a title, and it should be whatever our y variable is versus our x variable. So cost versus distance would be a suitable title for this graph. All of these functions that we're going to be having a look at are in contexts of certain problems. So we need to interpret the feature in the context of the problem. So for example, the first feature is that the y-intercept of the graph is 4. Here it is. It's not enough just to write that the y-intercept is 4. We need to interpret it in the context of the problem, and that is this description here, that the initial cost of hiring the taxi is $4 even before any distance is travelled. The gradient of the graph is 2. You can either work that out by looking at the common difference up here, or you can work it out by the slope here, so checking the rise and the run on the graph. So pick 2 points and find the rise and the run. The rise here is 2, the run is 1, so rise over run is going to be 2. In the context of the problem, however, that means that each additional kilometre travelled is going to cost another $2. That's what the slope means in this context. And the equation of the line equals C equals 2D plus 4. Sorry, that should have been pushed down onto the next line. And this means that the cost of a trip, which is C, is twice the number of kilometres, which is D, that we've travelled, plus another $4, which is our constant. So you need to be able to interpret these sorts of questions in the context, because you will only ever be asked to interpret them in the context. I don't want to know what the equation of the line is. I want to know what does the equation of the line mean in this context. It's an important distinction.